Welcome to an introductory video on the Bellman-Ford algorithm. This algorithm has the same objective as Dijkstra's algorithm, which is to find the shortest path from one source node to every other node in a weighted graph. However, it has one fewer constraint compared to Dijkstra's algorithm, which is that it allows negative edge weights. A constraint that applies to both Dijkstra's and Bellman-Ford is that the graph cannot have negative cycles. In this diagram below, we see a negative cycle from B going to A. But notice how if we keep cycling around from B to A, we can indefinitely reduce the cost of the path. So there's no concrete measure of the minimal cost for the path. So why is Bellman-Ford not constrained by negative edge weights? The reason behind this lies in the fact that Dijkstra's is greedy and Bellman-Ford is not greedy. So Dijkstra will always optimize locally, meaning it will always take the current lowest cost path based on the current vertex. So for example, if we imagine we're starting at vertex A, Dijkstra's will look at the path of length 2 and the path of length 3, and it will optimize locally and it will always choose the lowest cost path. So we'll go directly from A to B. But what this fails to do is it fails to get the overall correct minimal cost path of the weighted graph, which is going from A to C and then C to B, which has an overall cost of 1 unit as opposed to 2. The reason that Dijkstra's fails is because once it travels from A to B, it closes off B. Bellman-Ford, on the other hand, uses dynamic programming, meaning it'll explore all possible solutions and it'll choose the optimal one. So Bellman-Ford's algorithm will correctly identify the minimal cost path, which is indicated in the dotted lines. The time complexity for Dijkstra's is big O of E log V, and the time complexity for Bellman-Ford is big O of V times E. So Dijkstra will always perform better if the graph contains no negative edge weights. A key difference is that Dijkstra has only one iteration, meaning you're traversing the graph once. Bellman-Ford, on the other hand, has v-1 iterations. But what does v-1 actually represent? It represents the maximum possible path length given v nodes. So the maximal possible path length is v-1 edges, and we explore this by doing v-1 iterations. With each iteration, we're exploring an increased path length of 1. Starting from the first iteration, we will explore paths of length 1, and we'll continue to the v-1th iteration, in which we're exploring the maximum possible path length of v-1. That means we're covering all the possible permutations of different path lengths, and we're analyzing the entire picture. This is the essence of the dynamic programming paradigm. So why is v-1 the maximum possible path length? In this diagram below, we have 4 vertices, so v-1, which is supposedly the maximum possible path length, is 3. What if we have v or more edges? In the case of this diagram, if we have 4 or more edges, there must be a cycle, because there's a repeated vertex. Remember that Bellman-Ford terminates when it detects a negative cycle, since that's a constraint of the algorithm. Similarly, all positive cycles will only be adding additional distance, so we can ignore them completely, and that is a fundamental concept of this algorithm. So for each iteration, we have to relax every edge on the graph. So what does it mean to relax an edge? Well, let's take a look at this diagram below, which has 3 different vertices. Let's label node B as U and node C as V. And we have current distances of du equals -2, the cost of going from U to V as being -1, and d of V as being 4. So using this relaxation formula, we take the distance of U plus the cost of going from U to V, and we check if it's less than the current distance of V. And once we plug in those numbers, we realize that -2 plus -1 is indeed less than 4, meaning we have to update the new minimal distance, or minimal cost, to go to d of V. In summary, the Bellman-Ford algorithm performs v-1 iterations, relaxing each edge of the weighted graph until the minimum cost path from a single source node to every other node is determined.